Fingers crossed here. I can't hear you yet. Can you start talking?
Okay, can you hear me now?
Yes, very good. Thank you.
Okay, can you also see the slides, right?
Yes, we can see the slides. We can hear you. So the last talk in this session on web and web-based attacks, we'll hear Marco Squarcina from TU Vienna talk about the remote on the local exacerbating web attacks via service workers caches. Please go ahead.
So thanks a lot for the introduction. And it looks like the web tried to get revenge on me, as someone wrote in the chat. But yeah, I also got a backup computer in case things go wrong. So hi everyone, my name is Marco Squarcina. I'm from TU Wien. This is a joint work with Stefano Calzavara from Foscari, University of Venice. That was my former university, and Matteo Maffei from TU Wien. So I think that we all agree that the web is no more a simple content distribution platform. And the fact that we're having this nice conference inside our browser should be a solid argument, right? To convince you that the web morphed into an application platform nowadays. Progressive web applications are the latest trend in the evolution of the web. And this is mostly due to the fact that they offer a user experience that is similar to traditional applications by providing responsiveness and by supporting offline usage. Service workers are the key enabler of PWAs, since they act as a client-side web application proxy. A service worker can indeed intercept all HTTP requests made by the web application and also modify the responses with arbitrary content. Using the Cache API, service workers can also store HTTP responses and serve them at a later time. One thing also that is important to mention is that the service workers execute in a separate context from the JavaScript code that is running in the page. And that means that they have no access to the DOM. They also are not allowed to access cookies via document.cookie and cannot call other synchronous API calls like local storage or session storage. So let's now look in detail how caching is done. So this code snippet that is taken from the Mozilla website implements a basic version of a common pattern that is called cache first, that is used to minimize network traffic and provide offline capabilities. So we see in the first line that the service worker intercepts all the requests by registering a listener on the fetch event. Then it checks if the corresponding resource is found in the cache using the match method. If this is the case, the cache response is used, and otherwise, the resource is fetched from the network, and subsequently, it is added to the cache, first by opening a given cache, in this case, the name of the cache is static, and then by using the put method to store it inside the cache. And finally, as the last step, it is served back to the web application. All right, so our attack is enabled by the fact that, surprisingly, the service worker cache API is accessible from scripts running in the same origin where the service worker was registered. This means that an attacker with an XSS on a page can get arbitrary read and write access on the cached content for the whole origin. Okay, so what does it mean from a security standpoint? Well, an attacker can leak secrets from the cache, sensitive data left over from a previous authenticated session. And this includes personal information, multimedia content, security tokens, passwords, and so on. As we said, the attacker can also perform arbitrary corruption of the cache content, all right? And in this example, the attacker has reflected XSS on a page, so we make this assumption, but wants to spread a malicious payload to other cached resources. So let's now have a look. So in the first step, the attacker tampers with the cached responses in order to spread the injection of a malicious script, like a keylogger. Then the victim performs an access to a legitimate page, such as the login page, that happens to be in the cache. So this was like a page in the cache that was modified by the attacker. And at this point, the service worker will return the page that contains the keylogger, which will exfiltrate the login credentials. In a way, you might say that this is somehow similar to a persistent client-side XSS, because the attack allows to turn an ephemeral reflected XSS into a persistent attack. How persistent? Well, the cache does not expire unless explicitly cleaned. So even if the service worker is reinstalled, the cache is not modified by default. You have to explicitly delete it. As shown in this example, this attack can also be used to amplify the attack surface. And you can also mount a DOS attack by preventing the user from accessing the website. So you keep on returning the same resource over and over instead of the legitimate pages. So finger crossed, and let's try to see a demo. This is recorded anyway. So yes. Okay, so we create. Yeah, okay. To explain the attack. And Safe Notes is a kind of a poor man's Google Keep. It allows users to store personal notes. Each note is encrypted on the client with a password and stored in the browser. So there is no server-side counterpart here. It's just everything is on the client for simplicity. The website can also work offline thanks to the service worker that caches all static resources fetched by the browser. Then we also place the DOM-based XSS vulnerability on the page other.html. So let's have a look how the application works. So, okay, we are saving a super secret node with a password. Password is wrong, so the encryption failed. By putting the right password, we should be able to decrypt it. And yeah, and it works. Now we go to the other.html page, the one vulnerable to the DOM-based XSS vulnerability. And as you can see, if we inject an alert in the fragment, we successfully triggered an alert pop-up window. Okay, so what's the aim of the attacker? The aim of the attacker is to steal passwords typed by the user. The thing is that a traditional XSS wouldn't be very useful here, right? Because arbitrary code execution is restricted to the page other.html, and there is no possibility for the attacker to interfere with a sensitive page index.html. So going back to our attack, after the website is loaded and the index page is cached, as this is like the case, we assume that the victim clicks on our XSS payload. Let's see it in action. Okay, we also see at the bottom of the page that there are only two scripts that are loaded, safenotes.js and the one about the service worker. So now we simulate the victim clicking on the XSS, which is like this stuff, this bunch of stuff. So like this script registers a listener on the add a note button to read the password value from the DOM and prompts an alert message when the password with the password when the button is clicked. So let's see in action. Not so secure, not so secret node, now that I've been pwned. And yeah, you see that there is the alert message with the password that has just been exfiltrated. If we inspect the content of the cache using the Chrome DevTools, we can also see that the index page has been indeed modified to include our payload. Remember that there were only like two scripts at the bottom of the page. Now there is an inline script there that describes what I told you before about like this listener on the add button. Okay. So yes, okay, we are back to the slides. So we mentioned persistent client-side XSS before, but the ability of the attacker to perform person-in-the-middle attacks against cached responses opens up novel threats. Other than tampering with the body of HTTP responses, an attacker can investigate and manipulate the HTTP headers too. And this grants much more power than a persistent client-side XSS. For example, by disabling the frame ancestor directive or the content security policy or the X-frame option header, an attacker in control of evil.com could frame a page that was previously protected and mount attacks like clickjacking or certain classes of XS leaks. Other examples include breaking the document's isolation by removing the sandbox directive from iframes and the CSP. Also, stripping out the permission policy header in case it is enforced gives the ability to access the webcam and the microphone of the user. And furthermore, the injected script can be executed anywhere in the page. This is very important because this enables the attacker to bypass defensive programming practices such as freezing objects, which is a standard way to protect against the prototype pollution attacks. We wanted to check the pervasiveness of this threat, so we performed a large-scale assessment of the cache API usage by website. So we did this by using the pipeline that is shown in this slide. MITME proxy and Puppeteer for Google Chrome were used to inject a runtime monitor that keeps track of all the accesses to the cache happening in the page context and also inside the service workers. Then we said we saved all the recorded calls into a database for later analysis. For each one of the origin that we processed, we visited up to 50 different links in the same origin. So to speak, we did a lot of interaction with the website to maximize the coverage of our analysis. We also investigated the main subdomains of the sites in our dataset. Overall, we started from the trunk list and we crawled 150,000 websites for a total amount of 4 million distinct web pages. We found that service worker adoption as of last year, so this experiment was done in June 2020, is still low, around like 4.6%, but more than half of these sites are using the Cache API to store and retrieve data. So the Cache API is very often used in conjunction with the service workers. Since our threat model requires to have an XSS on the site, we analyzed the CSP adoption, and unsurprisingly, if you are familiar with web security, we found that the deployment is broken or completely missing in 96% of the websites that are using service workers and the Cache API. And yeah, in the study, we've only focused on websites with a trivially broken CSP. So if the site is well protected using the CSP, we didn't even try to exploit it. So then we came up with an automatic testing strategy to verify the potential exploitability of the issue in the wild. We visited a random selection of the links to fill the cache with some content. Then we infected all JavaScript and HTML files with our payload, and we also stripped out all security headers. After this step, we visited the pages again and checked whether our payload is executed. We performed this injection using an extension that we made available, and we found that our payload was blindly executed by 65% of the tested websites. Talking about countermeasures, how to protect against this attack. So a straightforward solution is to prevent scripts in the page to access the Cache API, basically restricting it to service worker context only. This is secure, but the solution would introduce compatibility issues on sites that are using the Cache API from the page context. From our measurements, we discovered that around 250 sites would be affected by this change. And furthermore, we identified some legitimate caching patterns that require cooperation between service workers and scripts in the page. So we propose to restrict the Cache API to service workers by default, but at the same time, we suggest a way to relax the protection using either a custom header or the new document policy, so to preserve compatibility. In a nutshell, you get a safe behavior by default, but also a way to opt into the current vulnerable design of the Cache API if you want, or if you need. As a mitigation, web developers can also harden the code of the service workers to protect against the malicious modifications of the cache. So not against inspection, but against the modification. This can be done by checking that the URL attribute of cached responses corresponds to the URL of the request. By doing so, it's possible to spot the tampering attempts because the synthetic responses have the URL attribute set to the empty string. But again, you will introduce compatibility issues. So to conclude, we introduced a powerful attack on service workers that revolves around the design of the cache API. We show that this attack grants person-in-the-middle capabilities that are more powerful than a persistent client-side XSS. Although our threat model is strong, we prove that it's realistic, considering that XSS are still very widespread, and mitigations such as CSP are not correctly implemented. Our large-scale assessment showed that 65% of the sites that are using service workers with the cache API are affected. And lastly, we proposed a backward-compatible redesign of the cache API that would immediately secure the large majority of the sites affected by the issue discussed in this talk. Just one other thing before concluding, the proof of concept examples, the extension, the paper, and also the slides of this talk will be published on this website, swv-attack.secpriv.wien. So thanks for listening, and I'm happy to take your questions.
Awesome. Thank you very much for the presentation. While folks are still typing their questions, let me kick it off.
Yeah, this is good for CTF challenge. That's definitely true. Yeah.
That's what I figured. The data you showed was from June 2020. Do you have an indication on how the numbers changed in, like, it's been like a year or so? Has this gotten more prevalent?
Sure. I think that the adoption of service workers and the cache API is increasing because PWAs now are really trendy. You can also install them inside the browser. Also, you can do the same on Android. So I guess that service workers are being adopted more and more, and so this kind of threat is there because there is no way to prevent an attacker from mounting this technique.
What about the mitigations? Did any of them make it into the major browsers? Do you see progress there?
No. This is a very good question. And we discussed with browser vendors and also with those behind the standard of service workers. We sent a paper, but we received no feedback. I think that our countermeasure is good in a way that it provides security by default, but security by default comes at the price of breaking applications by default. So It will require some applications to explicitly opt out from the mitigation. And so because the compatibility issue, I guess that this redesign is not taking place yet. The problem is that we are still in an early stage with the adoption of service workers, so it will be good to do it now before it's too late.
Right. But as we've seen time and time before, we first need more pressure through exploitation until this is actually being picked up.
Yeah,
because
sure.
This is not a major problem right now. It may take some additional time.
Yeah.
But yeah, super cool. I think you mentioned in the beginning, it's somewhat similar to client-side cross-site scripting, but it's I would see it more as a more powerful extension of client-side cross-site scripting that just gives you
because
additional
here you have
tools.
full person-in-the-middle capabilities that you don't have with traditional client-side XSS, persistent XSS. Sorry.
I agree. This is super cool. Thank you for the presentation.
Thanks. Thank you.
Drop the link in the chat so that other people can copy it and paste it. And yeah, thanks everybody in this session for your great talks. This has been a lot of fun, lots of interaction as well.